I'm going to talk about SARS-CoV-2 diagnostics, work that was really greatly advanced by the collaborative spirit at the Biohub, and especially our access to patient samples through the CLIA hub, which was a heroic effort very early in the pandemic by the Biohub to provide testing for the Bay Area. So next slide, please. Here we are, almost 2 years into the pandemic, but we're still in need of frequent, fast, and accurate COVID-19 testing. We needed to get our kids back to school. We needed to get back into the country, and we needed frequently to know our status in order to be safely around elderly or kids or those at high risk of severe disease. Next slide. There's in general three types of testing. The first is the molecular test. It's going after the viral RNA in the virus. The second is the antigen tests, testing for specific proteins like spike or N proteins. And both of those, the molecular and the antigen test, really are showing us whether we have acute infection currently, while the antibody test is a blood test that tells us whether we have been infected before or have been vaccinated before. Next slide. So the prototype of the molecular test is really the PCR test. It is highly accurate, while the antigen tests are less sensitive and more prone to false results. However, next slide, the PCR test takes longer. We all know that we wait on average about two days for the test to come back, while the antigen tests have the advantage that we can do them often at home, and we know within half an hour or an hour what is our result. So next slide. So when we set out to develop a diagnostic, we wanted it to have the accuracy of a PCR test with the speed and operational simplicity of an antigen test. Next slide. And when I say we, I really mean a team of 3 labs, Dan Fletcher, who you just heard speaking, and Jennifer Doudna. Both from UC Berkeley, both also affiliated with the Biohub and also with Gladstone. And we really wanted to combine our virology expertise here at Gladstone with Jennifer's Nobel-winning CRISPR technology and Dan's pioneering work in using mobile phones as diagnostics. Next slide. We started this work originally 3 years ago to develop a home test for HIV, and have recently pivoted it to SARS-CoV-2. However, the center of this test is really an enzyme, a CRISPR enzyme called Cas13a, that when guided with a small piece of RNA, which is called the guide RNA, which is complementary to the viral RNA in the assay, becomes targeted to that RNA and becomes activated. Next slide. And when it becomes activated, it becomes a nuclease and starts cleaving a reporter RNA, which when cleaved starts glowing, and that glow or fluorescence can then be detected by usually a large plate reader in the laboratory. So when Jennifer's lab published this in 2016, there was immediate interest in this technology, because it was the first time that we really could directly detect RNA without reverse transcription and amplification. However, it became also very clear that the sensitivity of that assay was not in the range of a PCR test. It was about in the range of 10,000 copies per microliter, while the PCR test is in the range of 1 copy of microliter that it can detect. So next slide. Very rapidly after that first report, group at the Broad Institute combined this technology with an amplification step, where a reverse transcription and amplification was preceding the detection with the Cas13 enzyme, and that lifted the sensitivity greatly. and allowed detection with a lateral flow assay, very much like we see today with the antigen testing. Next slide. But when we started this work 3 years ago, we decided to maintain the simplicity of the assay because we didn't want to add the cost, additional error, and time that the reverse transcription and amplification was bringing with itself. And we also did want to maintain the fluorescence outread, the fluorescence outread and the detection with a mobile phone as a mobile way to record it to improve sensitivity here. Next slide. So in January 2020, when the sequence for SARS-CoV-2 became available, we pivoted the work from HIV to SARS-CoV-2, and just based on the simple sequence, started to design these little guide RNAs that were, recognizing the SARS-CoV-2 RNA and could serve as a detection to help to guide the Cas13 enzyme to the virus. And you can see here some of these very early guide RNAs were very good, like guide RNA 2, for example, which has a very good response. The signal is very steep, and others were very bad, and the signal was very flat. However, it became very clear is that even the very good ones alone were not sufficient to have the sensitivity to become a diagnostic. Next slide. However, when we combined two good guides, we saw that we improved sensitivity quite a bit. And next slide. Currently, we're working with a vetted 8-guide combination that is recognizing all arising variants currently, but is not cross-reacting with any of the other viruses or with our human RNA in the nose. With this 8-guide RNA, we currently achieve a sensitivity of 10 copies per microliter, which is 1,000-fold better than what we started off with, and we can read this after 30 minutes of incubation. Next slide. One of the important things that helped us achieve this improvement in our sensitivity was that we changed how to read the assay. Normally, the assay was read with a normal endpoint assay, so at 10 minutes, 20 minutes, or 30 minutes, the reaction was stopped and the signal was read. We started to look at the slope of the curve that was induced by the fluorescence emission, and that allowed us to accelerate the time when we could call a reaction positive, but it also enhanced our sensitivity. Importantly, it made our readout time tunable by time, because samples with very high concentration of virus we could call immediately positive, while others with low ones we had to wait a little longer to call it positive. Next slide. Another very important advantage of this of the slope was that it is directly proportional to the amount of SARS-CoV-2 RNA in the sample. There's a very linear correlation here that allows us to directly call or deduct from our signal the concentration of the RNA in the sample. This is different from the PCR result, which is usually a so-called real-time PCR, where we use a cycle threshold to determine when the exponential curve is starting of the amplification, and that is used as a semi-quantitative measurement. Next slide. The second important step that helped us to improve the sensitivity and really come to the limit of detection where we are today was the mobile phone camera as a reader. This is really done by the lab of Dan Fletcher, where they turned this Google Pixel 4 phone basically into a mobile plate reader, using the camera of the phone aligned with the reaction, acquiring basically the fluorescence that is being emitted by the reaction as it is ongoing. Next slide. At the beginning, when we started with a mobile phone, the goal was really to make the phone as good as the plate reader. It turned out that the phone is actually 10 times better than the plate reader, and that is mainly because it is much more steady and less noisy in acquiring the signal, and that allows us to actually go about 10-fold more sensitive, and also accelerating the time to result. Next slide. This really combined with all the other improvement allowed us to use to use patient samples now from the CLIA hub with various amounts of viral loads in them, and call them as early as 5 minutes after incubation, 100% with 100% accuracy, positive or negative, to prove that this is really an accurate and fast way to measure SARS-CoV-2. Next slide. We have taken this technology now in different directions, from a fully automated cartridge to a low-cost modular user-driven system that Dan and I are very much supportive of, because it will give us the ability to distribute this widely and also make it potentially available in low-resource countries. And here we use basically manual force to push the reaction volumes into the detection chambers, and we maintain the benefit of the mobile phone to read these chambers and call a result. So the future is really to have a very compact and low-cost opportunity here that would allow potentially people at home to use their own mobile phones in the future to detect whether they're positive or negative for SARS-CoV-2. And all this, what I've told you so far, still keeps us as at a sensitivity of 10 copies per microliter, which is, as I told you before, still 10-fold higher than the limit of detection for the PCR, which is 1 copy per microliter. So to take this last step, next slide, please. Sunmin Son in Dan Fletcher's lab has really innovated a new technology where he takes the CRISPR technology into a droplet-based format by just simply emulsifying the reaction in a oil surfactant mixture, and then using an incubation time and a microscope to image and quantify the number of droplets. Next slide. This really results into droplets of different sizes. The key for this technology to work is that it's really a very small droplet size that is actually smaller than the usual ddPCR droplets that we are used to. But when these droplets are formed, we can, within between 0 and 10 minutes, clearly determine the number of droplets that contain a positive reaction in them. Next slide. So with the compaction of a large bulk reaction into a tiny little droplet, we could greatly enhance our sensitivity. And while the fluorescence or the signal per droplet is increasing over the incubation time, the number of droplets, which is really the outread that we're looking for, is fixed after only 5 minutes of incubation time and doesn't change anymore. So this really has very much shortened the time for the reading of the result. Next slide. Is that it has also enhanced our sensitivity. Now from when we use just one single guide, we have a sensitivity of about 20 copies per microliter that can be reliably read. However, if we combine guides now, like we are used to, next slide, with either 8 or even more guides, we can easily reach the level of 1 copy per microliter or even below in this assay. Now, sensitivity and time is not the only thing that we have gained with that droplet technology. Next slide. The fact that the individual guide RNAs that I have showed you very much at the beginning have these different slopes, either a very steep slope, that means it's a good guide, or the rather flat slope, which is a worse guide, is really something that we have used here as an individual kinetic signature, because this slope remains steady in the droplets independently from the input of the viral load, because each droplet always has 1 copy of the virus if it's positive. And so using this kinetic signature, that led us now to a new barcoding technology, next slide, where we use basically the different the slopes of the different guides to either distinguish between different viruses or to distinguish between different variants and wild type of SARS-CoV-2. And this is what I'm showing you here. We're using a guide that is specific for the variant, here in this case, the so-called California variant or the epsilon variant, which has a single point mutation that makes the reaction with the variant RNA much better than when the guide is recognizing the wild type RNA, which is here shown in purple. And so using just this kinetic signature as an outread, we were able to distinguish, next slide, with greater than 98% accuracy, patient samples that were either containing the wild type virus or the variant virus here in green. So next slide. In summary, we have shown that direct detection with CRISPR-Cas13a in bulk and droplet reactions is possible. We currently have a sensitivity of 10 copies per microliter in 30 minutes for the bulk reaction, and a sensitivity of 1 copy per microliter in 5 minutes for the droplet reaction. We have single molecule resolution in the droplets, which allows for kinetic barcoding for diagnostic, but it also allows very much for studies, basic studies of the kinetics of the Cas13a reaction. This barcoding, based on the guide target interaction, allows us to multiplex different targets now with a single reporter. Before, we had to divide the samples and put them into different reaction. Now we can do this in one single reaction with the same reporter and the same enzyme. And in general, this gives really unique quantitative capabilities for accurate, fast, and mobile RNA detection. Next slide. That we think in the future will be very helpful for many RNA viruses and other pathogens, which we have listed here and which are in various stages of development currently. But they will also in the future give us a new way of quantifying RNA that exceeds just viral diagnostics, but might go into biomarker or just general lab-based RNA quantification. So with this, I stop. Next slide. Thank the many people who have been instrumental to make this work. We have, the bulk work was really driven by Paranas Fizuni, an excellent MSTP student in my lab who has since graduated. And the droplet-based work, as I said, is being driven by Sunmin Son in Dan's lab. We have many collaborators in both labs, especially also Jennifer, her group, Dave Savage and Patrick Shu. We are indebted to the GLIA Hub members and many people at Biohub who has supported us with many different in many different aspects of the work. We thank Google for opening up the optics of the Google Pixel 4 phone to us in order to allow us to use it as a diagnostic. Bain, who has helped us with the device development, many who have lent their support, especially also the NIH RADx program, who have supported this work, and Biohub again for support, but also for providing a superb environment for us to do risky and hopefully successful work. Thank you.
With your ability now to identify different targets in the same reaction, is there evidence with SARS-CoV-2 diagnosis or with other viruses for improved either quality control or improved diagnosis if you are able to get a readout both of viral RNA load and also, for instance, one or more specific host transcripts?
Yes, excellent question. We are just getting into the question how well this would also work for mRNA, quantification. It is definitely we currently are doing a host gene as our positive control already, sort of a housekeeping gene that works very well, and so we anticipate that this can be expanded upon in the future, and specific markers can be tested here for certain cell types or others. But in general, I think we think that this technology far exceeds the potential of diagnostics and will be in the future hopefully quite disruptive for for other measures of RNA in medicine and biology.